Today we are going to talk about the Jordan canonical form of the matrix. Before going to the Jordan canonical form, let us try to understand why we need it and what it is good for. So to do this, let's first think about the rational canonical form of a matrix, which we've already seen. So what it says is that every matrix A, of course with entries in some field, is similar to a unique matrix of the form CF1, CF2, CFR, and zeros everywhere else. So this is a block diagonal form, and here these are polynomials f1, f2, fr, and we have f1 divides f2 divides fr. And this matrix CF is the companion matrix of the polynomial f, and so this is defined to be the matrix with the form. So if f of t is the polynomial t to the n plus a1 t to the n minus 1 plus an, then the CF is the matrix. Well, firstly it has ones just below the diagonal. It's an n by n matrix. And in the last column, you have the negatives of the coefficients of f. So you have here minus an minus 1 minus a1. The problem with the Jordan canonical form is, well, it does solve the similarity problem in the sense that you can check if two matrices are similar by computing their Jordan canonical, rational canonical forms. But the problem with the rational canonical form is that it obscures the nature of a matrix. Let's look at a very simple example of a matrix. So just take the matrix 2, 0, 0, 1. So if you take this matrix, then its rational canonical form is the matrix 0, 1. It's a companion matrix of its characteristic polynomial in this case, if you work it out. And its characteristic polynomial is t squared minus 3t plus 2. So it will be minus 2, 3. So that's the rational canonical form of this matrix 2, 0, 0, 1. So this very nice matrix, the fact that it has two distinct eigenvalues, namely 2 and 1, and that it's diagonalizable, all this is lost in the rational canonical form. From this rational canonical form, you cannot really understand anything about the matrix. So instead of the rational canonical form, we use the Jordan canonical form if we want to truly understand the nature of a matrix. And that's what we're going to see today. When we looked at the classification of finite abelian groups of a given order, then we saw that there were two ways to do it. And one was just to directly apply the structure theorem for finitely generated modules over a PID. And the other was to apply the structure theorem after first applying the primary decomposition. And the difference between rational canonical form and Jordan canonical form is the same. To obtain the Jordan canonical form, you first find the primary decomposition of your module corresponding to your matrix, and then after that you apply the rational canonical form to each part. Well, not quite the rational canonical form. The basis we use will be slightly different, as you shall see. So remember just this primary decomposition for a moment. So if you have M is an R module, then we defined and P is a prime element of R. Say R is a principal ideal domain. We'll be taking it to be polynomials. Then you can define MP to be M belonging to M such that p to the km equals 0 for some positive integer k. And this is called the p primary part of M. And M is said to be p primary if M is equal to MP. Okay, so and also we know that if M is a torsion module, which means that every element of M is killed by some element of the ring, then M is direct sum over all primes P in R, actually prime ideals P in R of MP. And here only finitely many of these MPs will be non-zero if M is finitely generated. So what does this say in the case of the kind of modules that we associate to matrices? So Jordan canonical form works over all kinds of fields, but in this course we'll just focus on algebraically closed fields. So let's take K to be an algebraically closed field. And the ring R in this case, the relevant ring R, is the ring of polynomials in K. So what are the prime elements of the polynomials in K? Well, we've seen that primes of R are basically linear polynomials, and so prime ideals of R, let's say, each one is generated by a monic polynomial. So each prime ideal is in the form T minus lambda for some lambda in the field K. These are the primes of R. So then you can talk about, so now given a matrix A, you can talk about its T minus lambda primary part. So remember that MA is just the KT module given by K to the N, and T dot V is just the action of A as a thinking of V as a column vector and multiplying it on the left by A. And now if you ask what is the T minus lambda primary part of A, this is V in Kn such that T minus lambda to the power K times V is 0. And this is sometimes called the lambda generalized eigenspace of A. So this is we usually denote it by V lambda, and it's called the generalized eigenspace for lambda. So in particular, if we take K equals 1, then we're saying that T minus lambda times V is 0, which is saying that, so this actually literally means that A minus lambda to the power KB is 0. So we take K equals 1, then this is saying that A times V is lambda times V, which is the definition of an eigenvector, V being an eigenvector. And so when we take K equals 1, then we get the eigenspace, and here, well, I should have said for some K greater than 0. So now if you take the space of all vectors V in Kn such that T minus lambda to the Kv is 0 for some K greater than 0, then you get something larger than the eigenspace for lambda, and it's called the generalized eigenspace. And so now what the primary decomposition says that this vector space K to the N on which the matrix acts is a direct sum over lambda in C of V lambda. Because on the face of it, this looks like an infinite direct sum, but it isn't, because the generalized eigenspace will be trivial but for all but finitely many lambda in C. And because k to the n is a finite dimensional vector space, so this is a finite direct sum. And now A takes v lambda into v lambda. Well, it may not be all of v lambda, well it usually is, but A takes v lambda into v lambda. We know that because v lambda is actually a submodule of M. And so let A lambda from v lambda to v lambda be the linear map obtained by restricting A to v lambda. Okay, and then what we have is that A can be written as similar to choose any basis of v lambda, then you will have A lambda 1, A lambda 2, A lambda M for some lambda 1 up to lambda M. So these are the lambdas for which v lambda is non-zero. And now what we need to do is to try to understand each of these parts, A lambda I, and try to give a canonical form for that. In order to do this, note that the module M A lambda, so let's just fix some lambda for which v lambda is non-zero, and then you look at the module M A lambda. Well, this, as we have seen, is T minus lambda primary. And its structure has to be of the form M A lambda has to be isomorphic to KT mod T minus lambda to the, let's say, K1 direct sum KT mod T minus lambda to the K2, and so on up to KT mod T minus lambda to the power KR. No other factors can occur. Basically, if you have KT mod PT occurring in a lambda primary module, then we've seen that that polynomial PT has to be a power of T minus lambda. So only powers of T minus lambda can occur in the decomposition of MA lambda. And now let's see how to understand one of these. So suppose we have M is KT mod T minus lambda raised to K for some integer K. Then we want to understand the action of T on this with respect to some basis. So take basis of KT mod T minus lambda to the K as E0 equals 1, the image of the polynomial 1 in this quotient, E1 equals T minus lambda, E2 equals T minus lambda squared, ek minus 1 equals T minus lambda to the power K minus 1. And then let's see how multiplication by T acts on this. So T EI is T into T minus lambda raised to I, which I can write as T minus lambda raised to I plus 1. So that's T minus I into T minus lambda, T minus lambda into T minus lambda raised to I. So to compensate for that, I must add a plus lambda T minus lambda raised to I. So that is just ei plus 1 plus lambda ei. So if you write down the matrix of this, then you have that T acts by the matrix. It has lambdas along the diagonals, and just below the diagonals it has ones. And we'll call this, it's a k by k matrix. We will call this matrix J k lambda. Such a matrix is called a Jordan block with eigenvalue lambda of size k. Okay, and these are the building blocks of matrices over an algebraically closed field. So let's just put everything together. So firstly, we have that A is similar to A lambda 1, A lambda m for some lambda 1, lambda m. So these are the lambdas for which v lambda I is not equal to 0. And then what we have is that A lambda I is similar to, well, so firstly, yeah, so k A lambda I, m A lambda I is isomorphic to kt mod t minus lambda I raised to k, well, let's call it I1 plus kt mod t minus lambda I raised to k I ri. And then on this block itself, let's just take some generic k here, or we could take kij. This is isomorphic to m subscript j lambda I comma kij, the Jordan block with oops, I think I have my subscripts, yeah, no, that's right, with eigenvalue lambda I and size kij. So finally, what we have is that the matrix A is similar to a matrix of the form. So firstly, you'll have j lambda 1 k11 up to j lambda 1 k1 r1, then j lambda 2 k21 j lambda 2 k2 r2, and so on up to j lambda m k m1 j lambda m k m rm. And zeros everywhere. So basically it's a block diagonal matrix, and the block diagonals are all Jordan blocks. Okay, let's look at a couple of examples to make all this more concrete and easier to understand. In particular, let's also see how to compute the Jordan canonical form of a matrix. So for this, let's start with a matrix which is in rational canonical form. So suppose A is a matrix in rational canonical form. And so MA is well, let's just say is A is a matrix such that MA is isomorphic to KT mod T minus 2 plus KT mod T minus 2 times T squared minus 5T plus 6. So this is basically giving us the rational canonical form of the matrix. So it's saying that A is similar to 2, and then there's this 2 by 2 block here, 0, 1, minus 6, 5. This is the rational canonical form of A. And from this, I'll show you how to derive the Jordan canonical form. So, so now let's factorize this polynomial here. So, so this t squared minus 5t plus 6 is t minus 2 into t minus 3. So, what if we want to break this up into primary parts, we need to separate out the t minus 2 primary part and the t minus 3 primary part. Now by the Chinese remainder theorem, what we get is kt mod t minus 2 into t minus 2 into t minus 3. That is this second factor over here, right? This piece is isomorphic to kt mod t minus 2 squared direct sum kt mod t minus 3. This is by the Chinese remainder theorem, right? And now we'll just collect all the parts with the t minus 2 factor and together, and keep the t minus 3 factors separately. So what we get is that MA is isomorphic to, well, so we have this kt mod t minus 2, and from here we have another kt mod t minus 2 squared. So we have kt mod t minus 2 plus kt mod t minus 2 squared, and this part is the 2 primary part, t minus 2 primary part, and then we have another factor here which is kt mod t minus 3, and this is the t minus 3 primary part. And writing down these parts separately will give us the Jordan canonical form of it. So we know that A is going to have Jordan canonical form. So firstly, this kt by t minus 2, that's just a 1 by 1 matrix with 2. Then this is kt by t minus 2 whole square, which we saw is given by this matrix 2, 2, 1, 0. That's a Jordan block of size 2. And then finally, there's a Jordan block corresponding to the eigenvalue 3, which is just this. So we get the Jordan canonical form of our matrix like this. So the blocks are, there's a 1 by 1 block here, and then we have a 2 primary part separated from a 3 primary part. Oops. So this upper left 3 by 3 is the 2 primary part. This thing here is the 3 primary part, And the two primary part has two parts, one of size 1, one Jordan block of size 1, and another Jordan block of size 2. Let's just do one more example to get this a little clearer. So again, we'll say that we know the matrix in rational canonical form. Okay, so we already know how to compute the rational canonical form of a matrix. So we'll use that as a starting point to get to the Jordan canonical form. So suppose A is in rational canonical form. Let's just take this one. This is a rational canonical form. Right, or better still is to see what the module is. MA, according to the structure theorem, is isomorphic to KT mod T squared minus 1 plus KT mod T squared minus 1. So the thing to do is to factorize these polynomials into their irreducible components. If we're working on an algebraically closed field, those will always be linear. So what we get is KT mod T squared minus 1 is T minus 1 into T plus 1, and so by the Chinese remainder theorem, this will be T minus 1 plus KT mod T plus 1, and then we will have another copy of this same thing. Now what you do is you must collect the same type of terms. So you get this is isomorphic to KT mod T minus 1 plus KT mod T minus 1, and then KT mod T plus 1 times KT mod T plus 1. And so the Jordan canonical form of A is read off from this. It has two Jordan blocks corresponding to 1, each of size 1. So that's just 1, 0, 0, 1, two Jordan blocks. And then it has two Jordan blocks corresponding to minus 1, each of size 1. Right, so the very simple nature of this matrix becomes evident from the Jordan canonical form. So inside I'm showing you the Jordan decomposition of each primary part, and there are two primary parts. So you can always compute the Jordan canonical form of a matrix from its rational canonical form by separating out the prime factors of each irreducible polynomial that occurs in the rational canonical form. And from the Jordan canonical form, you can read out most features of a matrix.